Next, we have an invited talk by Professor Debdeep Mukhopadhyay, Professor of Computer Science, IIT Kharagpur. Professor Debdeep Mukhopadhyay is an Institute Chair Professor at the Department of CSE, IIT Kharagpur, India. At IIT Kharagpur, he initiated Secured Embedded Agricultural Laboratory SEAL, focusing on hardware security. Prior to, he was a visiting professor in the School of Computer Engineering, NYU Abu Dhabi, and had visiting positions at NTU Singapore, NYU Shanghai, and Brooklyn. He was also an assistant professor at IIT Madras and held an adjunct position at IIT Bhubaneswar. He holds a PhD, MS, and a BTech from IIT Kharagpur. Dr. Mukhopadhyay has published more than 250 papers in peer-reviewed conferences and journals and is in editorial boards and program committees of several top journals and conferences. He is the recipient of the Shanti Swarup Bhatnagar Award 2021 for Science and Technology and is a fellow of Indian National Academy of Engineers. He was a fellow of C3I Hub, Innovation Hub of IIT Kanpur, and has been enlisted in Asia's most outstanding research compiled by Asian Scientist magazine. He was awarded the Qualcomm Faculty Award 2022, Khosla National Award from IIT Roorkee 2021, DST Swarna Jayanti Fellowship 2015 to 16, INSA Young Scientist Award, INAE Young Engineer Award, an associateship for the Indian Academy of Sciences, and a senior member of IEEE/ACM. Sir, please. I would like to request Dr. Anand Mohan to felicitate Sir with a shawl.
First of all, thank you very much for this kind invitation and also for this kind introduction. I will be giving this talk on post-quantum cryptography, but from the point of view of hardware security, which is essentially the area that I work on. So this is, like the lab that I essentially run in IIT Kharagpur, which is called as a Secured Embedded Architecture Lab. Our focus has been on attacks and countermeasures, specifically on the domain of hardware security and cryptographic engineering, which tries to take, like the theoretical foundations of cryptography and implement them on real life devices. And I've been happy to, graduate several very, good PhD students for whose good work, I'm presenting this talk. So this is how we started with working on. So we initially started to work on VLSI of crypto systems, worked on formal verifications for finite field circuits. Side channel analysis and countermeasures have been some of the central areas of our work. We also looked into post-quantum crypto implementations and still are looking into that because of its importance, as this conference also stresses upon. We have been working on microarchitectural attacks, Trojan designs and detections, physically unclonable functions, applying them on IoT security, machine learning for attacks and defenses, something that you cannot stay away these days away, cyber physical system security. And recently, I'm also interested in physical hardware assurance by imaging of hardware devices and also privacy enabling techniques, where many of these post-quantum techniques can be very nicely applied. So I'll give a very quick demo of our lab. So here is a quick view that you can have of our SEAL lab. Hopefully it works. There is an audio. No, it's not working. There should be an audio. Okay. So this is a sort of a setup that we have in our lab, where we are trying to kind of develop a hardware forensics setup. As you can see here, that there is a a scanning electron microscope, a FIB, and also an X-ray microscope, which we use to kind of monitor and kind of see into your hardware devices. And as you can understand that with this infrastructure, the objective is to look into the chips. Okay, so you can think about your small integrated circuits, maybe in your credit card. And what we are interested is really to kind of look into the device and see what kind of crypto circuits are really implemented. Okay. And the objective of this looking into is because of several hardware security threats, something that we called as hardware trojans, because many of these devices or chips are like fabricated at foreign shores, and we are always curious to know that whether they are exactly doing things that we want them to do, or essentially have something which are called as hardware trojans. So we do these imagings using also X-ray microscopes or XRMs, which essentially can probe your PCBs or your designs, which you can use in your data centers and other application areas. And what we are looking into is like whether these devices have components which can be potentially malicious. So this is one of the central thrusts of our lab, and we also have been, of course, working on things which are more classical hardware security problems, which are called as side channel attacks. I think so. Here are some pictures that you can see of PCBs which are being got from different sources. We are also looking into other applications, like for example, nowadays like security and cryptography have got several applications in the power security domain. So we are also building out like infrastructure for performing security evaluations of smart grids and like other real-time systems. We are of course interested in side channel attacks and fault attacks. So I think today morning we had a talk briefly being spoken by Angshuman where he was mentioning about fault attacks. So we are also looking into your chips, and which are basically like protected by the cryptographic techniques, and we are curious to know that whether like they can be broken by side channel evaluations or so. Our main objective is of course not to break the devices, but really to protect them and to kind of develop countermeasures which can potentially thwart such kind of attacks. So although we initially started to work on devices which are more, I would say, tailored for side channel attacks, but recently we are working on more real life devices which essentially are deployed in a commercial fashion. Okay. So here are and many of these hardware security experiments have to be done at rugged environments. Like for example, this is a temperature chamber that evaluates some of our hardware security primitives and kind of evaluates them at various temperature points. So this is an example of a fault attack setup that we have. I think Angshuman was mentioning about fault attacks, so we'll try to give you a quick view about how fault attacks work. So for example, here is a like a setup that you can see with an electromagnetic probe, and there is like an amplifier through which we can kind of amplify the like the EM pulses, and you can inject faults in circuits. Okay. So this is a kind of very quick overview about some of the lab infrastructure or hardware security that we work on. So with this background, I would rather get to the problem that we are discussing here, which is on post-quantum. We call it post-quantum cryptomania. Okay, because we know that the fear or whatever the apprehension of quantum computers essentially makes many of the foundational problems on which our current day public key resides vulnerable, and therefore we look into like potentials where we can develop cryptographic algorithms which are resistant even in the post-quantum crypto world. So if you look at what I will try to do in this talk is like come up with a, I would say, a 5-point recipe or 5-point step of how probably we can go ahead in designing post-quantum crypto, not only from the theoretical point of view, but also maybe like from the practical point of view or practitioner's point of view. So what we want from cryptography is, of course, we want informally to like protect our confidential data for being recovered by an adversary, and for that we often rely on hard mathematical problems. But however, most of these problems are based on assumptions that like the smartest algorithms which are existing in the world right now, they are not able to solve them in an efficient manner. So we call that in terminologies of computer science as polybounded in time and memory. Basically what it means is that they are efficient. So now when we look at quantum computers, or the problem or the post-quantum world, is that the quantum computers can solve many of these classical hard problems in an efficient manner. And therefore, when we step into the post-quantum world, we need to kind of develop techniques which are not only resistant against classical adversaries, but also quantum adversaries. Slightly formally, we call them being, like resistant to random oracle models, which essentially tries to kind of, simulate, I would say, an adversary in the classical world, and also what we call as quantum accessible random oracle models, which tries to model a quantum adversary. So in these both modes of adversaries, our system should be resistant. So for this, a potential roadmap could be envisaged in this manner. So in step one, we define a new hard problems or a set of new hard problems which are secured in the ROM or the quantum random oracle model, security models. And in step two, we try to develop crypto systems on top of it. Now again, like the statements are based on similar reductions that we see in the classical world, but now we are only relying on hard problems which are kind of believed to be secured in the ROM and the QRM security models. And in step three, we come up with parameters which can be used by these crypto systems for practical deploying for efficient implementations in software. But many of these algorithms are so complex that to make them real life or make them work in real life applications, you need support of hardware or hardware software co-design. And in this context comes the gap. Okay, comes the gap where adversaries tries to monitor things like side channels, like the power consumptions, the electromagnetic radiations, or maybe the behavior under faults, which can be used to kind of catastrophically break these crypto systems. So let's try to kind of take a very quick journey through these 5 steps. So in the first step, as I said, we need to define new hard problems. And as I think we have already been discussing about various types of hard problems like code-based, multivariate-based, and lattice-based. Of all these problems, like their classical counterparts, I would again emphasize are all assumptions, okay? So they are just believed to be impractical. So in particular, I will take a little bit of time to talk about lattice because the hardware that I will be talking about is based on lattice hardness. So we know that lattice is the regular array of points in space, and just to give you a kind of a quick view, probably it will look like this in a 2-grid in XY directions. And now what we essentially have probably like a basis which we can use to describe the lattice. And then we come up, suppose once we have decided upon the basis for the lattice, we are given a point P and asked to find out the lattice point Q that is closest to P. So now, while in the XY direction, it would probably not look very daunting, but the moment you start increasing the dimensions, this becomes harder and harder, or is at least believed to become harder and harder. So this is called what is known as the closest vector problem, and so on. Right, there are multiple similar problems which are believed to be hard in the ROM and in the QRM model. So noise and hardness has got a very nice association, it seems. Like if you take the very common algorithm like the greatest common divisor, which we probably all solve in our high school days, the problem becomes quite intricate when you introduce a little bit of noise, and this is called as the approximate common divisor problem. So the problem is that you essentially, if you little bit add noise and again ask for and generate what are called as approximate multiples of numbers, then finding out this GCD becomes more and more difficult. So this is exactly like the problem that we deal with. For example, here is a system of linear equations on the left, and on the right hand side are noisy versions of them. So it seems that solving the noisy versions are quite difficult. Like just to give you a very simple example for the uninitiated, like suppose you take a system of linear equations, and if you add a little bit of noise, as you can see here, and therefore these are not equalities but approximately equal, then the solutions can be significantly off from the actual results. And that apparently makes the problem more and more difficult on which you believe you to develop these problems. So for example, on the left hand side here, you can see a box which has been created using these noisy versions of samples. And on the right hand side, these are some random versions of the sample. And now, as we say, do in cryptography, we come up with various versions of them, like decisional problems or search versions. And these are believed to be kind of, like that even in the quantum world, we will not be able to distinguish between them. And that is what is called as the famous learning with errors or the LWE problem. So once you have defined or like discussed about these problems, you need to kind of like look into the hardness. For example, their hardness could be whether it's in the average case hardness or whether it's in the worst case hardness. Now, interestingly, lattice-based problems have probably worst case to average case reductions, and therefore they are pretty promising. On the other hand, when you implement these lattice-based schemes, you can also kind of nicely avail the nice ring structures and use techniques which are called as entity or number theoretic transforms through which you can get efficient implementations. Of course, code-based and multivariate systems, although they are lesser explored, have got also a lot of opportunities, and they are gradually coming up and becoming more and more researched. So the next thing, as we discussed, we have to kind of come up with the parameters, for example, the size of the key, the ciphertext dimensions, and so on which the crypto needs to be built. Now, once you have done that, you would like to build the crypto systems on the hard problem. And usually, as we will see that for many practical crypto systems, you have got techniques which are called as the key encapsulation mechanism, through which a session key is often established between parties, and digital signature schemes, which essentially are used by the counterparts to like sign and verify the signatures. Of course, post-quantum, along with it, and often lesser stressed, comes up with several other applications like privacy enabling techniques, where we develop techniques like fully homomorphic encryptions and so on. And along with it, there are like every day there are new crypto systems that are being built. So just to give you some examples, like key encapsulation mechanisms, as we know that NIST is currently standardizing it, but there are always like several algorithms every day being published which are based on these notions of hardness. Like just to give you some example, Kybird is a famous lattice-based algorithm which has been chosen for KEM for standardization. So likewise, for digital signature schemes, you have got techniques like dilithium and so on, which are used or are very popular and being chosen for standardizations for signatures. So after this, we would like to set up, like the parameters, and this is extremely important because on one hand, if I go for, and it's always a trade-off between security and efficiency, because if you choose small or conservative parameters, like we have seen in, like several contexts, like for example, we have seen in pairings, for example, which is known very well before. If you choose, small and conservative parameters, then often they have been broken by adversaries. On the other hand, if you choose large parameters, then your techniques or implementations or your solutions becomes inefficient. And, although you can kind of reasonably be sure about their security, but they are not very efficient. So therefore, the first choice could be that I choose very large parameters and I throw away all the compute power and parallelizations that are possible. Now, when we talk about resource constrained devices, like we were talking about lightweight public key, then this is not a nice strategy. And therefore, for that, we would probably try to kind of squeeze out the bit securities and efficiently do the trade-offs so that we can, implement them based on available compute power. And this is really, really a challenging problem. So in order to address the second, objective, we probably need hardware support for post-quantum protocols. And this brings us to the famous TLS-based architecture. Now in TLS, we know that it's a very common standard protocol for establishing secure communication on the internet. And classically, although, there are three very, I would say, clearly distinguishable parts, like the first part being the connection establishment, the second is the TLS handshake, and the third being the symmetric key cryptography. Now, we know that when we talk about the post-quantum problems, then the TLS handshake is the part that we need to address. So we wanted to investigate upon this and come up with a variant which we called as the post-quantum TLS and try to kind of protect it against the quantum adversaries. So we try to look at, again, the algorithms, and in this context, we basically pin down upon these two algorithms. One of them is called the Kybird, and the other one is called the dilithium. So this was a part of an MS student that one of my students was working on, and we tried to design a KGP PQC TLS, which is an agile post-quantum TLS accelerator, which encompasses, this is one point that I would like to stress, that because of the fact that quantum algorithms are getting compromised, you would need, even although we are going into hardware designs, you want agility. You want them to be supporting not only about, various algorithms, but also at the same time various security margins or security parameters. So therefore, our technique to implement this was essentially based on microcodes, which means that you would like to kind of implement them using like specialized instructions, and although it essentially like has the benefit of hardware, the underlying implementation has a lot of flexibility. So we came up with a design, and this design, in this design, we particularly looked at the various optimizations that are possible. Now I will try to give a warning here that optimizations can be really dangerous if we do not really understand the inner reasons for them. For example, we know that usually in this quantum in these implementations, there are repetitive computations, and one of the reasons why they are there because of certain security requirements, like what is called as the CCA2 security. So we cannot really remove those kind of redundancies, which otherwise would look like nice place for I would say like optimizations that are not knowledgeable about the underlying security. So therefore, the rule of thumb is that never optimize the algorithm, but try to kind of optimize the implementations. So in this context, let us try to take a quick look at Kyber and dilithium. This is a like a KEM algorithm. It has got steps like key generation, encapsulations, and decapsulations. And these are some of the parameters that Kyber has. Okay, and our implementation kind of caters to all these parameters. At the same time, we have dilithium, which is an algorithm of a different nature because it's a signature generation and verification algorithm, and it has got its own nature of parameters. So the first question that we needed to kind of address is how do you really combine this? So here we come up with a crypto coprocessor, which tries to kind of share the dilithium and the Kyber data paths and come up with like a memory-based orientation of these steps, so that you have got a combined KEM and at the same time a combined signature generation, which you can really apply in your TLS implementation. So we implemented this in a data path, and I'm just trying to kind of give you a very rough overview for the sake of time. So here we have got a hash unit, and there is a sampler, which is a very important component of our post-quantum implementations. Then you have got the entity multiplier, which I will a little bit talk about in my next slides, which are extremely important because they're the heart of your crypto processor. So what are entity multipliers? So just to give a very quick overview behind this, if I take two polynomials, and we really deal with very large polynomials in the post-quantum world, if you want to multiply them in the classical manner, then we have got an O(n) square complexity, because the usual way we describe the polynomials are with their coefficients. On the other hand, there is an alternative way of expressing the polynomials also, which is based on their evaluations. So rather than, for example, choosing like 4 coefficients in a 4-degree polynomial, you will probably evaluate the polynomial at 4 points and just multiply them in a point-to-point manner. And this gives you an O(n) kind of implementation. So therefore, the real crux is in transforming your polynomial, and here is where entity plays a role. So we looked at the corresponding entity for Kyber and found out that the prime essentially is in a manner so that it's kind of different from the entity that you have for dilithium, and because the prime is different. So the question was, how do you really unify them? And we came up with a unified architecture where till a point we essentially kind of shared the dilithium and the Kyber computations, but finally we follow the dilithium computation because it has got a higher degree by the additional step, which is based on the famous Karatsuba multiplier. Now in Karatsuba, I mean, I just give you this quick idea that it usually tries to kind of optimize the multiplications by corresponding additions, because additions are believed to be more efficient than multiplications. So with this background, we came up with a combined entity multiplier. The idea is that it can perform multiple entity multiplications at the same time, and it can also perform the forward entity, the inverse entity, and also the point-to-point multiplication in a very configurable manner. So the entity multiplier also interacts with a block memory, which essentially has got the input coefficients which are being stored, and that essentially provides an input feed to the entity multiplication. The other important step that we needed to look into was the hash functions, and we looked into the Keccak in this context because that was the primary block that we implemented, and essentially using the microcode based implementation, we can cater to various versions of SHA-3 and SHAKE, which are important hash functions which are used in these algorithms for various purposes, including pseudorandom generators. So finally, we came up with a parallel scheduling of the key generation of Kyber and dilithium. And you can see here, if you look into with care, you will be able to see that a lot of steps can be parallelized, but certain steps cannot be parallelized. And therefore, right, we came up with a, like an effective scheduling, which essentially can be performed with the reasonable hardware that we had afforded. So with all these things, we came up with a complete end-to-end implementations, and here are the kind of rough overview of the resources that are required on our platform. And in particular, in this particular target, which is an FPGA-based implementation, or a FPGA-based prototype, we can see here that the K-check and the entity multiplier forms the main components in the hardware design. And finally, this is the kind of comparison of our design with various counterparts. And as you can see here, that the area time product is really kind of, I would say, lucrative compared to the other designs. Area time product is important to measure because ideally you would like your hardware to have the least area and, to take the least time. But the area time roughly stays constant if you do not do innovations. And therefore, right, we believe that we have a fair amount of innovation to reduce the area time product of our design. So finally, after you are pretty satisfied with your hardware design, comes the important goal of protecting against side channels. So in side channels, it really doesn't try to kind of break your hardness of the problem, but tries to kind of have another side avenue to kind of know the secret key. But it is an extremely important vector because even NIST considers this as a part of their evaluation framework and tries to kind of evaluate the various side channel vulnerabilities. And that is one of the important criteria to choose one finalist over the other. Now, there can be various kinds of side channels. There can be passive adversaries, which basically tries to look at the power footprints. There can be active adversaries, which probably tries to actively inject faults in the computation and break your crypto systems. I will really not have time to talk about the passive adversary, but let me give a very quick overview about the active adversary and tell you how your crypto systems in the post-quantum world can be manipulated by very simple faults. So let us look at a potential KEM decapsulation algorithm and imagine that there is a fault that has been introduced, okay, which has been introduced here. Now, as you can see here, that there is this Fujisuki check which has been done, and this, one of the reasons you do this check, Fujisuki Okamoto check, which you do here, is basically to kind of enforce the CCS security. So the idea here is that if your fault is ineffective, then you will probably be here, and if the fault is effective, you will be in this area of your code. Now, the point is, the faults can be of two types, effective and ineffective. So let me try to give you a very quick overview in this context. So this is the decoding of Kyber. And as you can see here, that in this graph, there is this ciphertext space and the corresponding plain text. And this is how the kind of, if you properly choose your, inputs, then this is probably the distribution that it will look like. Now, the idea is that for this region, the decryption gives me 1, but for these regions, the decryption gives me 0. Now, suppose there is a fault and the fault skips an instruction. So this is the instruction which gets skipped, and because of which the distribution shift by around Q by 2. Okay, and Q is your parameter that you choose for your post-quantum implementation. Now, what happens because of this? You can see here, because of this shift, the green parts, as you can see here probably in the slide, you will see that they will be decrypted still to 1. If it was originally decrypted to 1, or if it was decrypted to 0, it still gets decrypted to 0, which means the fault is ineffective. On the other hand, for the red part, you can see that if it was decrypted to 1, now it gets decrypted to 0. And if here it was decrypted to 0, here it gets decrypted to 1. And this is an effective fault. So just by observing that whether the fault was effective or ineffective, you get to know the sign of the noise, okay? And as you know that in learning with errors, the error is extremely crucial, because if you have a notion about the sign of the noise, that means whether the noise is positive or negative, you can you can form systems of equations which can crack the key, okay? And therefore the entire crypto system will collapse. So therefore, it is important to protect against them, and there are a plethora of protections that people are coming up, but which also makes the cost higher. For example, you can shuffle the order of your computations, you can repeat the computations. These are all various strategies and countermeasures that you can try to kind of adopt. So finally, what is the future? Of course, we essentially are in a world where post-quantum crypto is extremely important, because we know that, there could be, adversaries which are harvesting now and will decrypt later. And therefore, it is an extremely important threat to our national security, and therefore, we need to kind of come up with protections. And what is the ideal transition step? So, yes, we will have standardizations, and standardization will grow, but it is extremely important to improve our understanding about the post-quantum crypto algorithms and come up with proper understanding so that we can also, like not only understand the hardness, but also come up with suitable designs. Because until unless we have suitable designs which are protected against, like side channel and other kind of lateral adversaries, we will not get an end-to-end design. So therefore, I would rather stop at this point, and if there are any questions, I would be very happy to address. You mean to say implementations? Yeah, so at this point in our designs, we have used entity-based decompositions. So, for example, for Kyber, we have used certain splits of entity, and we have used all these, like Cooley-Taki and normal algorithms, so that they essentially can be, like not only realize the functions but also make it efficient. So our objective was that we wanted to share the data path of dilithium and Kyber. And dilithium had a larger parameter, so we kind of, like used as much as possible both the data paths to compute both dilithium and Kyber. But for the final steps, we had used a Karatsuba-based decomposition.
Okay. Now another question, what are the vulnerable areas where you need side channel protection here? Because I read somewhere, compress, decompress. But are there any other areas or only those are sufficient?
So I would say that wherever your secret comes into play, and usually, right, like we have this S, right, which is a part of this. So wherever the secret comes in your computations, you need to kind of what are called do something which is called as masking. So you basically, like choose a random number and you try to mask your actual data. And in this algorithms, often you will have various arithmetic components, you will have Boolean components, so you need to choose appropriate masking. Like some of them will be arithmetic masking, some of them will be Boolean masking, and often, like these interoperating portions can be kind of tricky, like where you go from the arithmetic domain to the Boolean domain or vice versa. So we need to have suitable care over there.
There is a intriguing possibility, despite all the things you talked, I think were well taken, very nice. This harvest now thing, why not prevent it by every year double the RSA modulus? 2048 to, why double, quadruple? And I'll tell you why you can double it very easily, because anyway all this entity, everything is in play. They might as well play for modular exponentiation and RSAs. So my point is just this. I mean, of course, I don't know. You read new ones, new crypto, new stuff all the time, anyway, 20 years old. But if you scale the RSA ECDLP parameters by 4 to 8 to 16, use entity everywhere, you will still be reasonably well off, but preclude this quantum machines for some decades.
Yeah, I mean, I probably get what you're saying. I mean, I would also like to mention that one of the reasons why probably we should look into these class of crypto systems, again, I think as what was also mentioned, that these problems do not have as much history as probably the RSA problem, for example. Okay, so they are lesser studied in that context. But many of these designs, like which we do usually are matrix vector kind of operations, right? Because we do in LWE and those things, we multiply matrices with vectors and so on. But they can be often made efficient to be even more efficient than their pre-quantum versions actually. So I think not only from the security point of view, but if you properly optimize, then there is a good chance that if these post-quantum algorithms can actually become more efficient than their pre-quantum versions.
There you are right. Yeah. Because these post-quantum algorithms are subquadratic even, almost linear in some cases.
Exactly.
Whereas that will remain cubic.
And you can really parallelize them. You can parallelize these implementations.
Probably, and then with all your IoT and all that, maybe. Yes. Okay. So it's good to change over.
Yeah. That's also true. It is good to be ready. don't think there are any questions.
Any more questions? Thank you so much, sir. I would like to call Dr. Misbah, Scientist F, CDAC Bangalore, to felicitate sir with the memento.